children, hearty welcome to today's class. Last class, we were dealing about vapor pressure. Today, we are going to see the different factors which affect the vapor pressure. We know that what is vapor pressure. We have already seen that in the last class, that is the pressure exerted by the vapor when the rate of vaporization is equal to the rate of condensation. The pressure exerted by the vapor when the rate of vaporization is equal to the rate of condensation. All the theory and all we have seen in the last class. Today, here we are discussing about the factors which affect the vapor pressure. The factors are, one is intermolecular forces and the second one is temperature. The first factor is intermolecular forces and the second one is temperature. These are the two factors which affect the vapor pressure of the liquid. Now, let us see each factors one by one. If the intermolecular forces are small, then the vapor pressure will be high. That is the logic here. We know that in the case of vapor, in the case of liquids, the molecules are arranged like this and there are some free space, empty space between these molecules. And the molecules at the interior is having strong intermolecular forces, but the molecules at the surface is having not that much intermolecular forces because here there is no molecules in the up. Therefore, at the surface molecules are having not that much intermolecular forces compared to the molecules at the interior. So, here in the surface the intermolecular forces are small, therefore the surface molecules are having strong tendency to change from liquid state to gaseous state. Therefore, the intermolecular forces are one of the important factor for the vapor pressure. If the intermolecular forces are weak, then the molecules will be very easy to escape from the liquid state to the gaseous state. That means the rate at which the molecules escape will be high if the intermolecular forces are less. The rate at which molecules escape will thus be high. Rate is nothing but speed. So, if the intermolecular forces are low, the molecules can easily escape from the liquid state to the gaseous state. So, we know that some of the liquids are having they are very easy to escape from the liquid state to vapor state. Here we have an example of diethyl ether, ethanol and water. Here in the case of water, there is a hydrogen bonding between the oxygen and the hydrogen of the another water molecule. We saw in the last class, we will see here once again that one. Here we have ethanol. Here we have our diethyl ether. Okay. If we have a diethyl ether like this and we have water molecules like this and we have our ethanol like this, then if we look into these molecules, in the case of diethyl ether, this intermolecular forces is, the strength of this intermolecular forces is very little, or we can say that the intermolecular force is not there in the case of diethyl ether. There is no hydrogen bonding in the case of diethyl ether. Because of that, it is very easy to evaporate. In the case of ethanol, here there is a hydrogen bonding. Here when we look into water molecule, here the hydrogen bonding is so strong. Therefore, the intermolecular forces order in the diethyl ether, ethanol and water is having strong intermolecular forces, then ethanol, then we have diethyl ether. Water is having strong intermolecular forces, then ethanol, then we have our diethyl ether. So, if water is having strong intermolecular forces, what we can think about that? The vapor pressure or the water is very difficult to evaporate compared to ethanol and diethyl ether. So, the order of the vapor pressure of these liquids, water, ethanol and diethyl ether, is the reverse of the order of the intermolecular forces, that is, water is less than of ethanol, which is also less than diethyl ether. Therefore, we can say that water is the least volatile liquid, but diethyl ether is the most volatile liquid. Volatile is nothing but it can be easily evaporate. If we open diethyl ether bottle, then it will evaporate faster. If we open ethanol bottle, it will also evaporate fast. If we open water in a beaker, it will not evaporate that much fast because of the intermolecular forces are strong in the case of water compared to ethanol and diethyl ether. If we keep all these liquids open and we will come after 1 hour, the diethyl ether will be evaporated, liquid will be, diethyl ether will be evaporating, ethanol also will be evaporating, but water will evaporate very little. Okay, this is about the nature of the liquid or the intermolecular forces. This is the first factor which affect the vapor pressure. Next, we are going to see the next factor, that is temperature. Temperature is the second factor which affect the vapor pressure of liquid. The first point is that vapor pressure increases with increase in temperature. Vapor pressure increases with increase in temperature. The logic is that as we increase the temperature, what will happen? The kinetic energy of the molecules will be higher. If the kinetic energy of the molecules will be higher, means there won't be that much intermolecular attraction among molecules. Therefore, it can escape easily from the liquid state to the gaseous state. Okay, I hope you understood. When the liquid is allowed, when we boil the liquid, or if we apply some temperature, if we allow the liquid to heat, what will happen? The intermolecular forces will be lowering. Since the intermolecular forces are lowering, what will happen? The liquid molecules can easily change to the vaporized state. Therefore, what is the point is that the vapor pressure increases with the temperature. The higher the temperature, the higher the vapor pressure of a liquid. If we apply more temperature, then the vapor pressure will be higher. If we apply less temperature, that much vapor pressure only will be there. If we are not applying temperature, then the vapor pressure will be low compared to the higher temperature. So, the higher the temperature, the vapor pressure will be higher for a liquid. Then, sometimes we are seeing the boiling of the liquid. When boiling, what is happening? Boiling is occurring when the vapor pressure becomes equal to the atmospheric pressure. When the vapor pressure becomes equal to the external atmospheric pressure acting upon the surface of a liquid, it begins to boil. We know that here we have liquid, here we have surface of the liquid, and the molecules are here, and there are some empty space between the molecules. Then here there will be a vapor pressure. That means some of the liquid molecules are trying to escape from the liquid state to vapor state. Then what will happen? At particular time, the pressure is exerted when the equilibrium existing between the rate of vaporization to the rate of condensation. That time, what will happen? This vapor pressure will equal to the atmospheric pressure at the surface of the liquid. Here some molecules are there at the surface of the liquid, and here is some atmospheric pressure. Then for this surface liquids. So when this vapor pressure of the liquid is equal to the atmospheric pressure, the liquid will start to boil. I hope you understood what is boiling. Boiling is nothing but when the vapor pressure of a liquid is equal to the atmospheric pressure of the liquid at the surface. Here we have a definition for boiling point. The boiling point is the temperature at which the vapor pressure of a liquid becomes equal to the atmospheric pressure is known as boiling point. The temperature at which the vapor pressure of a liquid becomes equal to the atmospheric pressure is known as its boiling point. Boiling point is nothing but the temperature at which the vapor pressure of a liquid is equal to the atmospheric pressure. Then we have another two terms, that is, one is normal boiling point, another thing is standard boiling point. One is normal boiling point and second thing is standard boiling point. Normal boiling point is the temperature at which the vapor pressure of the liquid is equal to the 1 atmospheric pressure is called it as normal boiling point. So, normal boiling point is the temperature at which the vapor pressure of a liquid becomes equal to the 1 atmospheric pressure is known as its normal boiling point. For water, it is 100 degrees Celsius. So, if we take water, the normal boiling point of water is 100 degrees Celsius. And if we take the standard boiling point, the definition for standard boiling point is the temperature at which the vapor pressure of a liquid is equal to 1 bar pressure is called it as standard boiling point. The temperature at which the vapor pressure of a liquid becomes equal to 1 bar pressure is known as its standard boiling point. For water, the standard boiling point is 99.6 degrees Celsius. 99.6 degrees Celsius. One of the application of this is that at higher altitudes, the boiling point is decreasing. What is the reason for that? That is, at higher altitudes, what will happen? The atmospheric pressure will be low. Since the atmospheric pressure is low, the boiling point also will be low because the boiling point is nothing but the vapor pressure of a liquid is equal to the atmospheric pressure. At higher altitudes, liquids boil at temperature lower than their normal boiling points because the atmospheric pressure is low. If the atmospheric pressure is low, the boiling point also will be low. If the atmospheric pressure is high, the boiling point also will be high. Therefore, here in our southern states, if the boiling point of water is 100 degrees Celsius, at Mount Everest, the boiling point of water will be less than that of 100 degrees Celsius. That will be nearly 70 degrees Celsius. The reason is that at higher altitudes, the atmospheric pressure is low. Since the atmospheric pressure is low, the boiling point also will be low. We saw that the vapor pressure is increasing with the temperature. That we can see by in this graph. That is, here we have a diethyl ether. At 0 degrees Celsius, the vapor pressure of diethyl ether is 200. Then as the temperature increases, the vapor pressure also increases. And at a 760 vapor pressure, the boiling point is 34.6 degrees Celsius. That is the temperature where the vapor pressure of the liquid is equal to the atmospheric pressure for diethyl ether. And if we look here the ethanol also, in the case of ethanol also, the temperature, as the temperature increases, the vapor pressure also increases, and 78.3 degrees Celsius is the normal boiling point of ethanol. In the case of water also, as the temperature increases, the vapor pressure also increases, and the boiling point of water also 100 degree, water is 100 degrees Celsius. Then here we have an ethylene glycol. In the case of ethylene glycol, the vapor pressure is low. Vapor pressure is low as compared to the diethyl ether, ethyl alcohol and water. That is because the intermolecular forces are less. So that as the temperature increases, the vapor pressure also increases. This we can explain by one equation, that is our Clausius-Clapeyron equation or Clapeyron-Clausius equation. Clapeyron-Clausius equation. The equation is that P is equal to A e power minus delta H vaporization by RT. That is, P is equal to A e power minus delta H vaporization by RT. Here, P is the pressure, vapor pressure, A is a constant, delta H is heat of vaporization for the liquid, and that is the energy. Heat of vaporization is nothing but the energy required to change from liquid state to vapor state. That is nothing but the heat of vaporization, and R is gas constant, that is nothing but 8.314 joule per Kelvin per mole, and T is the temperature in Kelvin. This is Clausius-Clapeyron equation, and if we take logarithm of this equation, ln P is equal to this. If we take the logarithm, ln P is equal to ln A minus delta H vaporization by RT ln E. Then this ln E is nothing but 1. Therefore, this will be minus delta H vaporization by RT. And here ln A is nothing but we can take it as C. Therefore, the equation becomes ln P is equal to minus delta H vaporization by RT plus C. Ln P is equal to minus delta H V RT plus C. So here the delta H vaporization is nothing but the heat of vaporization required to change from liquid state to vapor state. Here if we plot the graph, that is ln P against 1 by T, we get a negative slope. That negative slope will be minus delta HV by R. This is the slope of the equation. So, if we plot a graph ln P against 1 by T, we get a slope of minus delta HV by R. And from this, this is x-axis, this is y-axis, and here we have x values. So, the slope can be calculated by y2 minus y1 divided by x2 minus x1. Here one value will be there, that is your x2. Here one value corresponding this one value will be there, that is our x1. And here one value will be there corresponding this here, that is our y1, and here one value will be there, that is our y2. So by plotting ln p against 1 by T, we can calculate the heat of vaporization of different liquids. Okay, then if we have different partial pressures and different temperatures, then how we can calculate, then how the Clapeyron equation will be, that we are going to see next. We have the Clapeyron equation as ln B is equal to minus delta HV RT plus C. So for ln P1, this will be T1. Then if it is for pressure, vapor pressure 2, the equation will be delta HV RT2 plus C. Okay. Now this is equation 1, this is equation 2. Now we can subtract equation 2 from 1, that is ln P2 minus ln P1. It will come ln P2 minus P1, that is nothing but ln P2 by P1 when we apply the logarithm rule. And here the equation becomes minus delta HV RT2 minus of minus delta HV by RT1, that is nothing but delta HV RT1. Okay, this will become as ln P2 by P1 is equal to plus delta HV R 1 by T1 minus 1 by T2. So the equation will be like this: ln P2 by P1 is equal to delta HV by R 1 by T1 minus 1 by T2. So if we take T1 and T2 as the denominator, then the equation becomes ln P2 by P1 is equal to delta HV by R, then here T2 minus T1 divided by T1 T2. Okay, so here if first we have to this T1 and T2 as a common denominator, then we have to divide the denominator by T1, then multiply, then we will get T2 here. The same way we have to do here also. Then the equation becomes delta HV by R into T2 minus T1 divided by T1 T2. So when we apply logarithm, the equation becomes log P2 by P1 is equal to delta HV by 2.303 R into T2 minus T1 divided by T1 T2. This is the Clapeyron equation when we have two vapor pressures and temperature. From this equation, if it is given like two temperatures and heat of vaporization and one vapor pressure, we can calculate the another vapor pressure. That we will do here. We have one problem here that we will do. Here the problem is calculate the vapor pressure of water in Newton per meter square at 90 degrees Celsius, given that its molar heat of vaporization is 41 kilojoule per mole and its normal boiling point is 100 degrees Celsius. 1 atmosphere is 1.01235 into 10 power 5 Newton per meter square. Here our aim is to find out the vapor pressure of water at 90 degrees Celsius. Vapor pressure of water at 100 degrees Celsius we have to calculate. And the given things are heat of vaporization is 41 kilojoule per mole. That for calculation we are converting to joule per mole. Okay, this we have to calculate. And here we have two temperatures. One is T1 that is 90 degrees Celsius, that is 273.90 is nothing but 363 Kelvin. And second thing is T2, that is 100 degrees Celsius, 273 plus 100, that is 373 Kelvin. Now we have pressure. One is, it is given that its normal boiling point is 100 degrees Celsius. So at 100 degrees Celsius means 1 atmospheric pressure. Therefore, P2 is 100 degrees Celsius, P2 is 1 atmosphere, then P1 we have to find out. So our equation is we have an equation log P2 by P1 is equal to delta H vaporization by 2.303 R T2 by T1 divided by T1 T2. So you have to substitute all the values here. P2 is 1, P1 we have to find out, and delta H vaporization value is nothing but 41,000 joule per mole, and here 2.303 into 8.314 joule per Kelvin per mole. Then here we have two temperatures, that is one we have to 373 minus 373 minus 363 divided by 373 into 363. Okay, we have to calculate this. Here we have 1 Kelvin, here we have 1 Kelvin. Therefore, this and this will get cancelled. Here 1 Kelvin is there, and this Kelvin and this Kelvin also will be getting cancelled. Then this mole and this mole also will be getting cancelled, and joule and this joule also will be getting cancelled. And finally, if we calculate all these things in our scientific calculator, we will get 1 P1 is equal to the antilog of 0.1581, that is nothing but 1.439, and here P1 is 1 by 1.1439, that is nothing but 0.6949 atmosphere. So our vapor pressure, initial vapor pressure is 0.69. The vapor pressure at 90 degrees Celsius is 0.6949 atmosphere. That we have to convert into Newton per meter square. That is what we have to multiply our value, that is 0.6949 to 1.01235 into 10 power 5 Newton per meter square. So when we multiply this 0.6949 into 1.01235 into 10 power 5 Newton per meter square, finally we will get the answer as 7.041 into 10 power 4 Newton per meter square. And finally, if we conclude the vapor pressure of the liquid affect two factors. One is intermolecular forces and the second one is temperature of the liquid. With this, we'll conclude this session here. We will see in the next class. Thank you.